Welcome to Lecture 8 of Algorithms. So today is a special day. So we've spent the past 7 lectures thinking about math, right? Dealing with problems in the ultra abstract. We've spent the time thinking about some very crude, very simplistic algorithms. But now today, you're finally going to learn your first sophisticated algorithm design technique, which is called divide and conquer. So here's the fundamental kind of philosophy, the guiding philosophy or guiding framework for divide and conquer. And this, to say that an algorithm is divide and conquer isn't to say that it is necessarily a fast algorithm, but it's just to put it under this umbrella of problems that we solve in the following way. So divide and conquer looks something like this. Here's the fundamental concept. So first, in a divide and conquer algorithm, you take the problem you're trying to solve and you break it up into chunks. Right? The number of chunks will vary. What a chunk means will vary from problem to problem. But this is kind of the step one of the overarching divide and conquer philosophy, is you break the problem into chunks. Sometimes it'll be obvious what a chunk is, like in an array algorithm. The chunk will typically be a subarray, just a direct subarray, but there's no reason to assume that it's as simple as that, right? So we'll see some other kinds of algorithms involving multiplication where the chunk is something quite different that is not obvious up front. So first you break it into chunks. 2, you go solve each chunk, right? Using the same algorithm. So there's often kind of a recursive flavor to divide and conquer algorithms. So you solve each chunk. And then 3, you take the solutions that you got from your recursion, the solutions to each chunk, and in some way you stitch them back together, or you use the solutions you got from the solved chunks to solve your original problem. So you use the chunk solutions, right? Whatever you get back from step 2, you use those to solve the original problem. So let's look at the simplest possible divide and conquer algorithm. Maybe this isn't the simplest possible, but this is a dirt simple divide and conquer algorithm. So the problem is the following, and it's a pretty simple problem. The problem is, given an array of numbers, what is the largest value in the array? What is max I in 0 to n minus 1 of a0, right? So this is the way of writing what's the largest value in the array. Right, so I write the max. The thing underneath the max in the underset there tells me what I am changing in order to find the maximum value. So I'm changing the array index. And then the thing after the max tells me what I'm actually trying to look at values of. So I'm looking at the values stored in the array, and I want to return the maximum value stored in the array. So notice this is not asking the argmax, which would return the index that gives me the largest element. Rather, it is just very simply giving me the largest element, right? What's the biggest thing in this array? Okay, so here's an approach. Okay, this is not meant to be a great approach, but it is an approach. So I'll call my algorithm max search. It's not really a search algorithm because search typically returns the index. So this is just, maybe I'll call it max find. Max find. So given an array with n elements, what max find will do is first it'll say if the array has only one element in it, so if n is 1, right, if there's only one element in the array, then I know what the maximum element is. It's the only element, right? So then if the array has length only 1, then you just return the only thing in the array. Then you just return a 0, right? The only thing in the array. Fair enough. Okay, otherwise, we'll do the following. Otherwise, we'll look at the left half of the array, and then we'll look at the right half of the array, and we'll return the larger of the maximum of the left half and the right half. So otherwise, we'll return the following. We'll return the maximum, right? So this is a binary max where it's just looking at two things, and it'll return the bigger one. So the maximum of max find the left half of the array, so a 0 to, and I'll see if I get my indexing right here, n over 2 minus 1. And notice I don't have a floor there, so I'll need to floor that. So if n is 2, then this just gives me the first element. Right? It just looks at the first half of the array, which is just a single element. So we say return the max of max find on the first half of the array, comma max find on the second half of the array. A n over 2 to n minus 1, right? And, you know, I won't go into the detail about whether or not the indexing works precisely here, but I invite you to take a look at it and see if you can find any issues with the indexing here. All right, so this is the algorithm. So what's actually happening here is it's saying, you know, let's just think of an array as being the following: 5, 4, 3, 1, 7, 8, 2. Let me do another one. So what it's doing is it's saying, you know, look, this array has 8 elements, so it doesn't fire the base case. So the first thing it'll do is it'll look at the left half, and it'll say go you know, process the left half, which is 5, 4, 3, 1, and then go process the right half. So 7, 8, 2, 1. And tell me what the largest value is in the left half, and tell me what the largest value is in the right half, and then I will look at I'll return the bigger of those two. Okay, so this is a recursive algorithm. So, you know, we don't get to actually return anything until we've hit the base case. But what it would do next is it would say, hey, look, I've got this array on the left, and I'll split that into 2, and I've got this array on the right, and I'll split that into 2, and I'll send this one down, 5 and 4, and then I'll send 3 and 1 down, and then I'll send 7 and 8 down, and then I'll send 2 and 1 down, and I'll ask, hey, you know, if I'm here, which of these has the larger number, and give me the largest number in that one. And then, you know, to this call, you'd say, hey, which has the largest number, and give me that one, and so on. And then I would go one more step, and I would say, well, here my 5 and my 4 get compared, and which one is larger? Well, 5 is larger, right? And then my 3 and my 1 get compared, and I'd say, which one is larger? Well, the 3 is larger, right? And so then the 5 and the 3 would get passed back up and then compared, and the 5 would win that one, and then it would get passed back up to get compared with whatever the maximum value was on the right. And so just for total completeness, we might as well finish this out. So the 7 and 8 get compared, and the 8 wins, and then the 2 and the 1 get compared, and the 2 wins, right? And so then these two get compared. So then we have 8 compared to 2, and the 8 wins, which gets passed back up, and then finally at the very end of it all, the 8 wins. And so what our algorithm would say is, after doing all this recursion, it would say, hey, the largest element in the overall array is 8, because it was the largest element in the right half of the array, which happened to be larger than the largest element in the left half of the array, and so on. So on all the way down to the base case, to the size 1 arrays. So here's our algorithm, right? We can see that it's a divide and conquer algorithm, because it takes a problem and then it splits the problem into equal size pieces. Right? It splits the problem into two equal sized chunks. I should say roughly equal sized chunks. And at some point in the next week or so, we'll talk about what happens if they aren't equal sized chunks and kind of how loosely we can consider that. But it splits the problem into two roughly equal sized chunks, goes and solves those chunks, and then solves the original problem using the solutions that it gets from the attempt to solve those individual chunks. So how do we analyze something like this, right? This is going to be the main thrust of the next few weeks, is trying to understand how do you come up with mathematical analysis for an algorithm that behaves in this fashion.